Good day, ECO235 students. We are in week 11, and this week we will start with topic 4, integral calculus. This topic will be done over the next 2 weeks. So we'll start it in week 11 and we will conclude this topic next week for week 12. All the work up to including next week's work is prescribed for your exam. And very importantly, the latter work that hasn't been tested extensively, you should expect your longer structured questions to come from this type of work. Now, in terms of the prescribed readings, you can consult Chapter 10, Section 10.1 of your prescribed textbook, or the Jacques textbook is a supplementary reading, Chapter 6, Section 6.1. And this deals with indefinite integrals. Next week, you will deal with definite integrals. So for this week, we'll look at the meaning of integration as well as indefinite integrals. And next week, we will see definite integrals and the application of integration on economic problems. So because this is an introduction into this topic, the rules that you are going to be exposed to will be fairly basic. However, in the postgraduate mathematical economics module at honors level, all the applications, including work dealt with in matrices, etc., becomes a lot more advanced. Now we need to understand what is integration. And for this week, as I've said, we are going to look at indefinite integration. Now, can you think of a pair of operations in mathematics which cancels each other out? So for example, if you think of multiplication and division, if I give you the number 3, keep that as your original number, and I say, right, take number 3 and multiply it by 2, you're going to get the answer 6. But if you then divide 6 by 2, you get 3. So the two operations cancelled each other, and what you ended up with was the original number you had started with. Now, in this example, it was necessary that the non-zero constant was the same, and in this case it was 2. But now, of course, in mathematics, there are other operations where they are inverses of each other, not as simple as the example as I just gave you. There is another example where there are inverse operations of each other, and you are going to deal with one such example now. So up until now, from your first year microeconomics, you have been dealing with differentiation. Now, the inverse operation of differentiation is called integration. Now, suppose that you are given a function f of x and it is equal to x to the power of 3. Now, you know that your first order derivative f prime x or f dash of x is going to be 3x squared. Remember, you would differentiate, you'd bring the power down, multiply it by the coefficient 1 to get 3. Then you multiply it by the variable x. Then your power becomes 3 minus 1 or n minus 1. That would give you 2. Now, notice the notation. This is going to be important for our notation for integrals. See that typically you would use f prime x or f dash of x to denote the first order derivative of f of x. But here we are going to use the lowercase f to indicate that it is the derivative of this function f of x. Now let's ask ourselves, what if you were given 3x squared and you needed to find the function that differentiates to 3x squared? So you need to work backwards to get x cubed. This is again an easy example because you know that to differentiate you would have said n minus 1, which gave you that 2. So therefore, you can work backwards by saying n plus 1, 2 plus 1 would give you 3. And you also know that if this coefficient is 3, it implies that you would have had 1 as the coefficient here because 1 times 3 would give you 3. So to work backwards, it would mean that this coefficient would have had to have been 1. Hence, working backwards, our answer was x cubed. But most examples are not going to be so simple. So you're going to have to learn how to reverse this process of differentiation by doing integral calculus or the process of integration. So you are going to need to understand and recognize the notation for indefinite integration and then later on definite integration, and then also some basic rules. It can become quite complicated as well, but for ECO235, since we only do it over 2 very short weeks, it is kept quite basic. So in general, if f of x or f dash of x is equal to f of x, notice here the difference in the notation. So here I'm using a lowercase f to indicate that it is the first derivative of a function f of x, right? So this lowercase f of x is the same as this, and it's indicating that it's the first order derivative of this function f of x with this capital F. Then it's said to be the integral of f of x. So this is said to be the integral of f of x. So other names for the integral here of f of x is referring to this as the antiderivative or the primitive. Since this is your derivative, this is then the antiderivative. Remember the reverse operation. So therefore, it can be written as f of x is equal to the indefinite integral of f of x dx, or with respect to x. So in our previous example, we would say the indefinite integral of 3x squared dx is equal to x cubed. There's your antiderivative, which was the integral of your derivative here, right? So this curly long s is the integral sign, and this dx is also important. Very often students forget about the dx, but almost view this as brackets. So whatever is in between your integral sign and the dx is what you are going to be performing the operation. So in essence, we wanted to get the reverse operation of this. This was that derivative. We wanted to get the integral of that, or the antiderivative, which we saw was x cubed. So to recap, this notation of your indefinite integral sign and the dx is just here to tell us that we need to think of a function that differentiates to whatever is inside of the integral sign and dx. And what it yields is f of x plus c. Remember, f of x was this antiderivative, but what is this plus c? Where did that come from? So c is referred to as the constant of integration. So in the previous example, our antiderivative or primitive or integral was x cubed, right? For f of x. But what if there was some constant that had differentiated to 0? If there was a constant 2 plus 2, when you differentiate, you know that constants differentiate to 0. So that would have fallen away. And we would not have known that, given that we are just given the first order derivative. Hence, we always add this constant of integration. So then in general, if f of x is a function that differentiates to f of x over here, then so does f of x plus c. The following points just highlight how to read this notation. So if you have your long curly s, your integral sign, with your f of x dx, it means the indefinite integral, that, of f of x with respect to x, or dx. And as I said, the symbol is the integral sign. So yes, I'm saying the indefinite integral. It is very important to distinguish what this sign looks like versus the notation when we speak of definite integrals. And we'll come to that in next week. But typically just the sign with no values in the superscript and subscript, it tells us that we are looking at indefinite integrals. Now, the lowercase f of x is called the integrand. That is this bit that is in between your integral sign and dx. So that is called the integrand. And your uppercase f of x is the integral. And I like the word antiderivative because we know what a derivative is. So it makes sense to think of an antiderivative of the opposite of that. So that is this uppercase f of x. And as we said, c is that constant of integration. So if f of x is the integral of f prime x or f of x, then there are these rules for indefinite integrals. So these are just basic rules. They are much more advanced rules, but we are just going to look at some very basics. And what you will notice is the operations are very similar to, for instance, your power function rule with differentiation, for instance, or where you sum or get the difference when you perform differentiation as well. You'll find similarities between these rules, just we are reversing the process. So as we said, f of x is equal to the indefinite integral of f of x, this lowercase f of x, with respect to x or dx. So next week, as I said, our final topic will be on definite integrals. Now, the difference between the two is that when you perform the operation of indefinite integrals, what you end up with is still a function. We are going to be given, let's say, a marginal cost function or a marginal revenue function, and we have to work back to get the total cost or total revenue function or total product function. But you end up with a function. Whereas with definite integrals, what you end up with is a number. So that number typically represents the area under a curve, and you determine that between limits. So whereas here we just have this integral sign, there's no lower limit or upper limit. With definite integrals, you're going to notice that there is a superscript and a subscript, and that represents the limits of integration. And then we can actually determine things such as producer surplus and consumer surplus. And that will be the final application that you do next week. So I'm going to pause here and I'll continue the next video by discussing the following rules.